Hello, so today we'll talk about this very nasty looking, very intimidating looking integral. And this integral is actually from Putnam. And yeah, when you look at it first, it looks very formidable, like how are you gonna tackle this kind of integral? But the awesome thing is the moment you begin looking at the structure, of the polynomial inside the natural logarithm, and you look at the limits, so for example, you look at the behavior of 9 minus x, okay? So as it goes from the limits 2 to 4, okay? So 9 minus x behaves from, so from 2, it acquires the value of 7, all right? And then as you go to the final limit, which is 4, it goes to, so that's 9 minus 4, it goes to 5, okay? On the other hand, the other expression that you see here is, so you have in the denominator 9 minus x, the other one is x plus 3, okay? And so x plus 3, if you go through the limits from 2 to 4, x plus 3 goes from a value of 5, and then going to 4, it goes to a value of 7, okay? So the property of this expression is 9 minus x as it goes from 2 to 4, and then x plus 3 as it goes from 2 to 4, it kind of reverses, okay? And so it would be nice if we can simplify our original integral in such a way that we can get rid of the denominator altogether, So in order to do that, this is just a very clever substitution, and we do the following, okay? So we want our integral after doing a variable substitution to look something very symmetric. So in particular, okay, we will do the following substitution, okay? We let y be equal to, okay, 6 minus x, okay? So why are we doing this substitution? So the thing is, when we do this substitution, look what happens to your 9 minus x, okay? So your 9 minus x, when you do this substitution, 9 minus x, if you substitute for x for y, okay, so from here, if you let y equal 6 minus x, obviously that implies that x is equal to, what's that, 6 minus y, okay? And so from that substitution, the 9 minus x equation, it actually becomes, so you have 9 minus 6 minus y. So that becomes 3 plus y, okay? And why do we need that 3 plus y? So because that 3 plus y looks like the x plus 3 that we have above. And of course, also, the x plus 3, after doing this substitution, this becomes 6 minus y plus 3. It becomes 9 minus y, okay? And so I hope you can see where we're going here. The original integral in the numerator, it involves the expression 9 minus x. In the denominator, you have 9 minus x and x plus 3. So what we're doing is we change variables, okay, by looking at the property that the ranges that they assume kind of reverses the role when you go over the limits from 2 to 4, okay? So what happens is when you effect the variable substitution, let x be equal to 6 minus y, what happens is the expression in the numerator becomes of the form variable plus 3, and then in the denominator it kind of looks the same, okay? So let's do that variable substitution. So after substituting the variable, our integral becomes the denominator first, so the ln of 9 minus x, from here we showed that it becomes 3 plus y, or y plus 3, okay? And then the other expression, you have the square root of ln x plus 3. We show that x plus 3 after the substitution of variables becomes 9 minus y, okay? And of course, you have in the numerator, square root of ln of 9 minus x becomes the square root of ln of y plus 3, okay? What happens to your dx? Well, your dx is simply negative dy, okay? And what happens to the limits? Well, when x is equal to 2, y becomes 4, right? Okay, when x equals 2, y becomes 4. And when x equals 4, y becomes, because y is 6 minus x, y becomes 2. Okay, so it reverses the limits, because like we said, the expressions inside, the two expressions, 9 minus x and x plus 3, they have this property that the limits that they go through, the values that they assume, kind of reverses the role as you go from the limit 2 up to 4. Okay, so now we have minus dy, so let's just get rid of that minus sign by reversing the limit. So this becomes 2 to 4, ln of y plus 3 square root plus ln of 9 minus y square root, and then in the numerator you have ln y plus 3 square root, and then you have dy. So you got rid of the minus sign because you reversed the integral sign. Okay, so again, this is very important. This is still the original integral. Okay, we just change variable. Okay, so however, the variable is the letter y is a dummy variable. I can call it anything I want. In fact, I can call it x, right? So this will become integral 2 to 4. I can call this y. I can call it, instead of y, I'll call it x. So you have ln of x plus 3 plus integral or square root of ln 9 minus x, and then in the numerator you have square root of ln x plus 3. Okay, so you have that, and then instead of dy, it becomes dx. Okay, again, this is still the original integral, but look what happens now in the original expression. The numerator becomes different, but then their denominator are the same. Okay, so we take this integral, our original integral that we have on top, we add this to this same integral, but now with a different numerator on top. But again, we claim that this has the same this is the same integral as the one above. We just changed variable to y, and then that y we just converted it to that same variable x. Okay, so now if I add these two variables, these two integrals, I will get 2i, correct? Because I'm adding both of them, and see the magic here. So what happens is this becomes the integral from 2 to 4 of the integral above. Okay, this integral right here, this will be our first term. So that is square root of, so you have ln 9 minus x plus the square root of ln of x plus 3, and then in the numerator there you have square root of ln 9 minus x. Okay, we're adding it with, so this is the x, we're adding it with this integral right here, which will claim to be the same integral as the one above. So this will be square root of ln of x plus 3 plus the square root of ln of 9 minus x. And again, in the numerator, we now have ln of x plus 3. Okay? So now, when you add the two of them, look what happens. It's very cool. So again, the limit is 2 to 4. So when you add the two of them, so now you have in the numerator, you have ln of 9 minus x plus ln of x plus 3. Okay? And since, sorry, let me prop up my tablet again. It fell down. So that's why my handwriting looks kind of weird, because I'm kind of angling the tablet so that it can still be seen in the camera. But anyway, so in the numerator you have ln of x plus 3, and of course we are able to do that addition. Why? Because they have the same denominator. Okay, so you can just like add the numerator like a way that we did right there. So we have that addition, dx. So now the numerator and denominator cancels. That is the magic right there, okay? So this becomes integral from 2 to 4 of dx, which is of course x evaluated from 2 to 4, which is of course just equal to 2, okay? But this is 2i, right? So in other words, the original integral, okay, is just equal to 1. What? Man, so this original integral right here that looks very formidable, this is actually just equal to 1, okay? And in fact, we can check that. We can use an integrator, a numerical integrator, just to show you that it really gives you the value 1, okay? So let me zoom this out a little bit. So let me go here, and then let's do integrate. Okay, so what was our expression? Our expression was the square root. So the square root of ln of 9. So we have 9 minus x. So x is our variable. And then we divide that whole thing by, so we divide it by the square root of ln of still 9 minus x, and then it has another term which is, so that's plus the square root of the ln of x plus 3. Okay, so let's check. All right, you have that, and then you are integrating x from 2 to 4. Okay, and let's evaluate this. Oh, sorry, I pressed enter instead of like evaluate. So let me delete that and let us, how do you evaluate this? This one. Okay, there. So it's equal to 1. Okay, so the integral is equal to 1. So however, if you notice, there's nothing like actually special about this. So the only thing that is special about the function square root of ln of 9 minus x and the square root of ln of x plus 3 is that they are continuous from 2 to 4. Okay, so between the 2 to 4, their values don't become infinite, or they don't get like some crazy values. Okay, they're not discontinuous from 2 to 4. Okay, that's their only property that we're requiring. So in other words, we can go crazy. So let's write it here. So we can go crazy instead of our function being just of the form square root of ln of x. Okay, we claim that you can use the same technique if you have an integral, for example, from 2 to 4, any function of the form f of, what was that in the numerator, 9 plus x over f of 9 minus x plus f of x plus 3 dx. You can use exactly the same technique that we've applied before, so long as the f of 9 minus x plus f of x plus 3, these functions are continuous from the intervals 2 to 4, and of course we have to require that f of 9 of x plus f of x plus 3, the one in the denominator, of course, it shouldn't be equal to 0. Otherwise, you will have a divergent integral. Okay. So, for example, you have the integral of 2 to 4. Let's see, I don't know, some crazy functions like, let's say, sine cube of 9 minus x over sine cube of 9 minus x plus sine cube of x plus 3. Okay. This is equal to 1. Right? How do you do that? You use the exact same method that we did. You just substitute x for 6 minus y, and then you do the same thing. You still obtain the same integration value. And in fact, when we evaluate that here, when we integrate, so just to make sure that that we are right, so we evaluate sine of, what's that? 9 minus x, and then let me put a parenthesis on the whole thing because we're gonna raise it to the third. Okay, so the whole thing raised to the power of, let me figure out if I can find the exponent here, raised to the power of 3 divided by sine of 9 minus x, and then raised to the power of 3. So raised to the power of 3, and then plus another sine of this time x plus 3 raised to the power of 3. Okay, and then again we evaluate x from 2 to 4. Okay, and then press enter. Bam! It's still equal to 1. Okay, so again, as long as your function is continuous, you can be as crazy as you want. So you can give this like as an assignment. You solve tan of, I don't know, cos of 9 minus x over the tan of cos of 9 minus x plus tan of cos of x plus 3. What's this? This is still equal to 1. Okay, this is still equal to 1. So what you do is, again, you do the same technique that we did above. You let x be equal to 6 minus y, and then you get an integral that is exactly the original integral, but now with a y variable, you change that dummy variable to x, you add the two of them, you cancel the numerator and the denominator, it gives you a value of 1. And again, just to hammer it in, okay, just to make sure that we're not fooling ourselves, we go tan cos of 9 minus x, and then divide the whole thing by, so divided by tan of cos of 9 minus x, okay, and then plus tan of cos of x plus 3, okay, and we evaluate that integral again from x to 4. Okay, when you press enter, boom, it's still equal to 1. So yeah, so again, initially the integral looks very intimidating. So our integral right here, let me make this 100%. So our integral on top right here, it looks initially very intimidating, but once you look what happens within the expression and then from the, the limits, it's actually, very, very straightforward. So yeah, it's the integrals looks contrived, that you knew that's gonna happen, but yeah, that's the beauty of like mathematics. And of course, even though when you say that the whole thing is contrived to behave this way, that is still one less definite integral to worry about. Okay, so I hope you learned something today, and I'll end my video here. I'll see you next time. Thanks for watching. Bye bye.